Hello, I'm going to be talking about bit flipping key encapsulation today, and this is my presentation. So, quick overview of quantum computers. Quantum computers are computers that use qubits instead of bits. Qubits are different than regular bits because they have properties such as superposition, which means they could be a 0 or a 1 at the same time. But whenever they're measured, then that's when they have to be either a 0 or a 1. They also have entanglement property, which means that if two bits are entangled, a 1, for example, is entangled to a 0, then if the 1 becomes a 0, the 0 will instantaneously know that the other bit became a 0 and it will become a 1. So it kind of mirrors the entangled bit. These two properties, such as being multiple values at once and entanglement, will make mathematical computations much faster. For example, prime factorization. So why are quantum computers a threat? Quantum computers can perform factorization in polynomial time for prime numbers. That means that most modern cryptography standard algorithms will become obsolete because they are based on prime factorization. For example, they're based on the mathematical hard problem that it's easy to multiply two prime numbers, but it's hard to factorize them. But with quantum computers, it's easy to factorize them using an algorithm such as Shor's algorithm. So experts estimate that it may take 20 years to switch all of our cryptography standards on devices after finding quantum secure standards. So that's why we're starting post-quantum cryptography now. So what is BIKE? BIKE is a code-based cryptography. It was submitted into NIST, Quantum Cryptography Standardization, and NIST is looking for encapsulation mechanisms and digital signature schemes in order to get quantum resistant versions of those. So BIKE is a key encapsulation mechanism that is code based, meaning it uses error correction codes. Error correction codes are used in communication systems. For example, sending bits and it becomes corrupt, and then you can correct those corruptions using error correction codes. So why is BIKE important? BIKE is quantum resistant. Understanding BIKE now may help us develop other methods of quantum security. And quantum proof cryptography is urgent. BIKE is also currently one of the finalists in the NIST standardization process for post-quantum cryptography. BIKE does have one version, BIKE 2, that has keys, a shared key, a private key and a public key that can be reused. And recent hardware implementations have been shown to be secure against side channel attacks. So what is the BIKE procedure? So let's say we have a sender and a receiver. So the sender will get the public key from the receiver, and then the sender will encode a message using the receiver's public key and insert some errors into it. And this is switched, so it'll then go to them. It'll go from here to there to the public channel once it has the errors. And then a parity check matrix will be used to correct the errors using parity bits. So the error correction mechanism here is used as the private key, and the original message is then received. Let's go to byte key generation. So byte generates keys that depend on the level of security that you want. We have a public key that uses a generator matrix, and a private key that uses parity check matrix. So we have level 1 byte, which is not really secure, level 3 byte, and level 5 byte, which has the same security level as AES 256, which means that it has bit security 128, and it'll take 2 to the 128 iterations to crack this code on a quantum computer. So byte public key. Okay, so byte uses quasi-cyclic codes, which means that let's say I have 10100. I know that the next row in my matrix is going to be 01010. How do I know that? Because I shifted the bits by 1, and then I shift them again. This means that we can define a matrix using a single row, which is much more efficient than having to write out a whole matrix, and it will help reduce the key size for public keys, which is a really big problem in a Michaela system, which does not use quasi-cyclic codes. Okay, so byte private key. Byte's private key is a parity check matrix. A parity check matrix is used in many error correcting technologies used today. For example, by that I mean if I want to send 1000 to somebody, during the transmission it might become corrupt and it might have a 1 in the middle. But then we can use a parity check matrix, which are like linear codes, to correct back the message to 1000 for the receiver. How does it do this? Well, first we can say that this original message has an odd amount of 1s. So let's say we can add a 1 at the end to say now it has an even amount. So that's our parity bit. And let's say this 1 is connected to this here somehow, and if we now have the parity check here and we know this is supposed to be an even amount and it's connected to this bit, then we can easily correct the error. So what about in terms of cryptography? Parity bits can be used as a secret key, and the sender of a message can purposely insert errors. So in cryptography it's used kind of like, I want to send a message, but I'm going to purposely insert errors, and the receiver knows how to correct those errors. So anybody trying to listen in on the public channel will not be able to know what the true message is. So byte ciphertext. Ciphertext is created by using the encoding function with the public key and turning the message into a code word. So here, the ciphertext is created with inserting errors using the public key and decapsulation. The byte ciphertext can then be decapsulated using the private key, which is a parity check matrix that the receiver has only. The parity check matrix, again, is a thing that corrects the errors. So why is this quantum resistant? This is quantum resistant because quantum computers are really good at things like prime factorization, which have one answer, while parity check matrix might have multiple answers. However, only one or a couple of parity check matrices will be good enough that they can get the message in a feasible amount of time. So the attacker might also get different answers that are considered bad matrices that would make the decoding the word or the message take an extraordinarily amount of time. So byte side channel. The byte system is secure from side channel attacks such as timing and power analysis. This is because a byte block of code can be run in parallel. So if somebody tries to see how much power is consumed from each block of code, all the blocks of code are run in parallel, so it's hard to know how much each block individually consumes. Also, byte has a decoder that runs for a fixed number of rounds for a fixed time. This prevents timing attacks, which means like timing the amount of time certain computational operations take. But since it takes a fixed amount of time, a fixed amount of time, you can't time the amount. So what is the underlying mathematical problem for byte? So byte relies on the fact that it's really easy to insert errors into something, but it's really hard to know what the errors in something are. For example, I inserted into 1000 11, let's say I converted it into 1111 by a bunch of errors. It's really easy to insert these errors, but let's say I just tell you my code word is 1111 and I'll tell you what are the errors. It's really hard to reverse this. So here's an example. I use a 5-bit word and a 5x11 matrix. It gives me 11-bit word, which means I have 6 overhead bits, and I can correct 3 errors, which means I can correct half the amount I have of overhead bits. Okay, and the public key is created using the private key multiplied by a random variable. So here, public key multiplied by the message through matrix multiplication plus random error. So now I'm going to go through a quick demo on byte. So here I have my secret key, my private key variable, my public key variable, my ciphertext variable, and my shared secret for the sender and the receiver. This code checks to see if the receiver and the sender both have the same shared secret. So let's run the code. Here you can see my code ran. This is the ciphertext here. You can see C1C0 stands for my ciphertext. And then here you can see my private key, which is the error correction bits. You can see which bits are the ones that were changed. H0, H1. Here is my public key, which was created using the secret key. You can see it's much different than the secret key. And then the result is that the shared secret between the sender and the receiver are both the same, which means it was encrypted and decrypted correctly using the encryption mechanism here that gives you a ciphertext, and the decryption mechanism here that it takes in the ciphertext and decrypts it. Okay, so here my implementation results. You can see that bike has a short length for a private key and a large length for a public key and a ciphertext, which is due to the matrix multiplication. This means that it would be really good for situations where another device could take most of the decapsulation and the key generation work, while a device such as a phone or something will only focus on the encapsulation. Okay, here are my references for my presentation. These are the websites I used, and that's it. Goodbye.